Welcome back. This is the third and last video of section 2.1, in which we are going to prove the continuous differentiability of the inverse function. So this is a generalization of the familiar and elementary result that the function from r without 0 to r, which is given by 1 over t, is of course c1, and its derivative is minus 1 over t squared. So here's the result. If you have now we need the condition of completeness, because why the completeness? So far we were working in just any normal space, but now we need completeness because first of all we need E and F to be isomorphic in order to ensure that this set is not empty. And the Banach condition, if you recall, ensures that this set is open. Okay. So if you consider the map from the set of isomorphism from E to F into the set of linear bounded maps from F to E, this map that each S associates the inverse, this map is C1. And its derivative is at any increment H is given by minus S minus. So the inverse of S times H times the inverse of S. So this is really a generation of this because in the if F equal R, then this is commutative. In general, this is not commutative because this is just the composition of operators. Okay. But if they were commutative, then you get S minus 2H. So get. Now, just to understand what's happening here, this composition map is really from F to E because we start from this S minus, so S minus 1, then H, then S minus 1. Okay. The first S minus 1 takes me from F to E because S takes me from E to F. So S minus 1 takes me from F to E, and then H takes me from E to F, and then back to E again. Okay. So this is very important. And later we can replace this by, instead of S minus 1, I can define a general bilinear map where I put here an operator T and here an operator L, let us say. Okay, so same diagram. Okay, so we go back to the definition. Okay, so we take an increment in the open set of isomorphisms, which is small enough, and we have to find a linear approximation of this increment. So the difference, if you go back to the definition, this is the inverse of S plus H minus the inverse of S. Now we do a trick. SS minus 1 is the identity of what? This is a map from F to E and then from E to F. So this is the identity of F actually. And S plus, so the composition of S plus H and its inverse is what? Is the identity from E to E, because this takes me from E to F and then from F to E back. So this is the identity of F, this is the identity on E. Okay. Now, I noticed that there is a common factor here, first of all. S plus H minus 1 is now a common factor, so I can factor by it. Okay. And I have to the right S minus 1, so I can factor by S minus 1. So double factorization gives me S plus H minus 1 to the left and S minus 1 to the right. And in between, we have S here and S plus H here. Okay. And the difference is, of course, minus H. Now, by linearity, I can put the minus H outside. So this is because everything is linear. No. And that's it. Now, when we do the difference of, because this is, I want to prove that this is the derivative. So I write the difference between F and its approximation. So F of S plus H minus, so phi of S plus H minus phi of S minus this linear map in H, of course, as you may check, this is linear. And of course bounded. So we get what? We get the difference between this operator encountered here and this one, but I have the minus outside. Okay. And you guessed what I wanted to go to, where I want to go. I want to prove that this difference is a small o of h, or small o of the norm of h. Okay. This is the strategy. But this is easy because here again I can factor. I have the hs minus 1 in common, and I am left with the inverse of s plus h minus the inverse of s, which is just the difference between the image of s plus h under phi. And okay, and now it's straightforward because now if we take the norm, so this is a small o of h. Why? This is really easy to prove because just take the norms, okay, and the operator norm, because we are working here. Everything happens now in what? In the space of linear bound operators from F to E, okay, because we are in the image now. So take the norm in the operator norm in L of Fe. And we know that we proved in the first chapter that the norm of a product or a composition is less than the product of the norms. So when I take the norm, okay, this is the composition of three maps, s minus 1, h, and this difference. So the norm of the minus doesn't change anything. So the norm of this difference is less than the norm of phi s plus h minus phi of s times the norm of h times the norm of s. And now continuity of phi that we proved in chapter 1 tells me that this is really norm of h times something that tends to 0. So this tends to 0. And so therefore this is a small o of h by definition. Okay, so this proves that phi is differentiable and its Frechet derivative is given by this map. And well, we have to check something, that this is really as a function of h is continuous, and it's of course it's linear because everything I'm composing linear maps. So if you like, if you put instead of h1 plus h2, you'll convince yourself that you get. So this is linear in h, clearly. If you multiply by a constant, you can put it outside. So this is really linear in h. I didn't write that, but you can do it actually as an exercise. So this, as a function of h, is linear, and it's bounded. Why? Also, this follows from this fundamental inequality. When you take the norm, you will get the norm of phi prime of sh is less than norm of s minus 1 times norm of h times norm of s minus 1. So this proves the boundedness of phi as a function of h. Okay, because here we have to distinguish between two things: continuity in h and continuity in s, which is something different. Okay, continuity in h is very easy, straightforward. You have to write it here. I didn't write it, but straightforward. Okay, and now I have to show that I have to show continuity in s. Now, the derivative operator is what acts from the set of isomorphism, which is the open set, into what? This is a little bit complicated space, but this is the space of linear bounded maps from the set of linear bounded maps from E to F into the set of linear bounded maps from F to E. Okay, so you'll get used to that. So it's not terrible. So I want to prove that this map is continuous, and of course it makes sense to talk about continuity because this is a topological space, it inherits the norm, and this is of course is equipped with the operator norm. So okay. How do I prove that? Okay, I prove that phi prime is obtained by a composition of continuous maps, as you may check. So first of all, we consider a bilinear map from this product. So the first component is a linear bound map from F to E. The second component, same thing, and the value is a linear bounded maps between these two. So this is the operator psi. Okay, so psi is a function of two variables, t and l. T is here, l is here, same thing, and the value is actually a linear map again. So it acts. So I take h to be an element here, and the result would be an element here. So here you can go to the diagram. Okay, so first I go from L takes me from F to E, and H takes me from E to F, and T takes me back to F. So this is really a map from F to E. Okay, from F. So F, F, E, E, F, F, E. okay, as in the previous diagram. So this is the action of psi TL on H, okay? And now it's easy to check that as a function of TL, it's bilinear, okay? Because it's linear in each variable. So put T instead of T, T1 plus T2, and then instead of L, same, because it's symmetric, and to multiply by a constant put outside. So it's really easy to check that psi is bilinear, and it's indeed continuous, and the norm of psi TL is less than the product of the norm. So the norm of psi is less or equal than 1. Okay, so, and now finally, if I put instead of T and L S minus 1, so I compose, so then phi prime of S is precisely psi of S minus 1 S minus 1, which is psi, first component being phi, the second component being phi. So actually, phi prime is a composition of, phi is continuous and psi is continuous, so their composition is continuous actually. If you like, this is, we go from S to the couple phi S, and then we compose by psi. So it's a composition of continuous map, so it's continuous. Okay, so don't confuse continuity in H, which is a little bit simpler, and continuity of in S, which is a little bit more complicated because we have to, but not terribly difficult. Okay, so this proves that phi is of class C1. Okay, so this concludes this video and section 2.1. In the next section, we are going to prove some expected result about rules of differentiation. Okay, so some product composition and so on. Okay, so thank you for your attention and see you next time.